So my topic is about talking about engineering in industrial environments in industrial automation, especially with OPC UA. And I would like to start with the big picture that Peter was showing in the beginning of his talk. And as you see here, this is a quite interesting complex system where OPC UA is used throughout a plant manufacturing and process automation, for communication, also for getting to information, for modeling information. And more and more, the domain is expanding here. And if you look at this, you may have the question how this gets all created. I mean, how this gets all be set up, who has to work together here to make this happen, and how do we bring the data and finally the information, so engineering to the plant. And this is another dimension that is not shown here, but it's exactly something that when UAFX was started was another important point, that we also look into the life cycle of the systems in order to give guidance and to give rules how they will happen. Yeah. And this is also, that's brought UFX also to the decision that we have to support, or we have to go into offline engineering. We have to make ideas about engineering tools. We have to provide even maybe software tools for supporting engineering in a plant. And this is was for the beginning seen as one important step. And as you see here, the technologies used. One technology that came new into the OPC UA world is here the AutomationML, which is an engineering language and for modeling information for a wide area of engineering topics, which is far going over that what OPC UA is currently doing. And so the interesting challenge of this project was to also to bring the AutomationML modeling and language together with what OPC UA is offering, the OPC UA information model. This project was started in a project group that in the end created the Part 83 standard of UFX. And going a little bit, making a little bit more point on this, as you see here, the classic value chain for a plant is selecting products, selecting automation devices, and integrating them into a larger module system, and finally bring them to the plant and wire everything together and press the start button, power it up, and then it should run. But it will only run if you do a planning before, and this is this orange chain here, which is in parallel ongoing. I mean, everything you do, you plan in a digital way before with some tools. Even if you have not procured yet the hardware, you have to deal with the devices. You have to select your products on some paper information. You have to create the engineering of your controllers, maybe without the controllers even in place, and later, of course, bring this together with the hardware. So this is a little bit the digital value chain that is accompanying the real value chain where you make the production site happen. And here, a new concept was developed in the UFX, which is called the descriptor, which is a way to share and to encode the information you create during engineering. It's not a digital twin. I mean, we in the beginning, we discussed going also this direction. It's more a kind of data collection information model that helps you to keep your information together. But it's not it's not as high level as a digital twin, but I think it could be also contributing to a digital twin in the future. Let's going, and here you see a little bit the thing that with our project group tries to bridge we try to bridge current industrial engineering, which uses a lot of different modeling concepts. We try to bring this to the online running stuff, the UA server, where the OPC UA information model is there, where the communication happens. So we try to bring this together and make a fusion out of that. And as I said, the two concepts that we're inventing here is on the one hand side, the descriptor as a kind of container for collecting and sharing information of engineering, and the other is a kind of it's a mapping where we bring the OPC UA information model language together with the AutomationML language. And this going a little bit into detail about where a descriptor is used and what is the basic use case, a kind of baby use case for sharing information. This is one of our first examples we did. It's about creating a control engineering project. So a control engineer A would do some configuration for a controller which may not exist yet, and to share this information with another engineer for another controller. And within this data that gets shared, there is the information, what data a controller exposes, what data it needs, and the other engineer can then provide the necessary information and receiving input-output configurations to consume or provide the data needed. And this is all handled based on the UFX concept, on the asset concept we have, and on the functional entities to describe these interfaces. It is based on some descriptors that are coming from from automation vendors, because you need a kind of startup with your engineering, and these two descriptors here describing the products that are to be used in the project. So this was our first step, but as you see in a real project, a lot of things get exchanged. The exchange happens quite complex. You may not want to integrate one controller. You have multiple controllers from multiple vendors to integrate, and it gets more and more complex. And but this is a basic step that we defined as a start for the information exchange. So what is a descriptor? This is an interesting question. So we are basing the descriptor on the AutomationML concept of an AMLX container, which this is already part of AutomationML. It's basically, you could say, a zip file. And we have a little bit two types of basic information. The one is formalized information that is derived from an OPC UA information model encoded in AutomationML. This is one of the big chunks here. And the other thing is a kind of open package container where you can attach vendor-specific documents like drawings, manuals, even data sheets, and then you can even have a kind of descriptor in descriptor that is a little bit a hierarchical way to put information together. You can have links to all kind of contents. We have some manifest that identifies the whole thing. And in the end, we are requiring that we have a digital signature on each container so that you know from who has created it. This is already defined. It was released in part 83 already, and we described this concept. We described the rules, how to do this. We have some information on how engineering tools should work with this. It's based on the Open Packaging Convention standard that was created by Microsoft. It is used also in some areas, like, for example, in the Office documents. It's used in AutomationML. It's used in asset administration shell. It's also used in MTP. So it has a big acceptance in the industrial world. And we're using the AutomationML language, which is also a long-term accepted standard for engineering. And as I said, we also allow, the concept is open for vendor-specific content. So that things that needs to be shared but are not yet encoded in information models can be also included. So, and now I would like to talk a little bit about the phase 2, which is the controller to device in OPC UA, and where we have, starting from existing UFX concept, we want to get much more concrete and a little bit more stringent also, and have how to handle parameterization, networking diagnostics, and also look into the area of motion, I/O, and instrumentation. And there are two things that, when we started looking into this, that are quite important and critical, to where we need to provide more information to the engineering OPC UA world. And these are two things that we need to handle products in a better way than we currently doing. And therefore, we have a kind of sub-concept of the descriptor that is called product descriptor. And this is exactly where you start, that a product descriptor you would like to use to start the engineering phase. So this is a very important start step. Without having that, you would always start writing a descriptor from scratch. And so that is, of course, not efficient enough. The other thing that is a little bit related to this, and I will explain this in a moment, is about constraints. We have an OPC UA, a very flexible and comprehensive information model based on types, on attributes, and on properties, references, and so on. If you know this in more detail, you know that it's a good way for modeling information, but it's more like of a kind of static modeling, and it's sometimes lacks the flexibility to express a specific engineering need. For example, every time you want to restrict the range of a value, you need to invent a new type, an enumeration or a specific range type. And so you will, the closer you come to reality with your information modeling, the more you need to invent types, additional objects, and so on. And this gets a little bit of kind in a more kind of explosion of your modeling. And therefore, we think another approach, or an additional approach, could be also helpful here in order to derive more precise information, and we call this the constraints. And this is a concept that where we think it will highly improve the quality in the engineering, and in the end also help to be more efficient in offline engineering, and bring a better engineering results, so that things that in the plant can be started up without more modifications, and you don't have to go back to the engineering table for doing things. So product descriptor itself, this is a concept that is also highly, I would say, coupled to the OPC Foundation infrastructure, like that in OPC Foundation has a product catalog, OPC Foundation has a kind of certification of the devices. So in this kind of, if you have a product descriptor, you will deliver together with your hardware, the product descriptor. You see this on the right picture. The vendors will deliver together with the device also a descriptor, this digital sheet, to the OPC Foundation for certification. In the certification process, it will be checked that these product descriptors contain the same data that is in the hardware, and they describe the capability needed for engineering. So it's about capabilities, it's about types and ranges, and so this will be certified. And in the end, also these descriptors will be uploaded. Here it's mostly by the automation component vendors, also on the OPC Foundation website, where we make available with links. And so it will be part of the OPC Foundation catalog. And so customers are able to browse this catalog, are able to get to the data of the product descriptor. They can maybe compare things in the product descriptor. They can even work with the products that are contained there. And they have all this information available without looking at the hardware. So this is one of our main goals, describing this process with the product descriptor structure in the next phase. And what is also here a little bit important, that when we discuss what is a product is not only one fixed thing that you buy. A product is also something where you select during your procurement process. So if you buy a t-shirt, you look for the size, you look for the color. So a product also has a close connection to a concept called product family, where you have the specific variants for the product. So you have some selection criteria where you can select things, and in the end you define the exact variant, and a product code comes out. Or a product can be also a modular product that in the selection of the what you will to buy, you have to select some components that can be added or removed. That is, for example, also needed when you go for I/O stations, where you have a family of modules where you can select how many I/O modules you want, analog I/O, digital I/O. You can add this to your basket, and so the product descriptor should also contain this kind of selection information, and the ranges or the attributes, the selection information, what you want to select, the dimensions, and what kind of ranges you have. It could contain the components that you will add to your product, and so it will also be define this kind of flexible process. And for that also, I'm coming a little bit to the next slide. That is also something where we have the constraints, rules and constraints. See it as a use case here for defining these kind of product families. In the end, if you look what it is, a product descriptor is nothing else than a descriptor. So it has an information model. It has attachments, it has a signature by the manufacturer, but it's basically something that comes from the automation component vendor. It's not coming from somebody else. So it needs to be signed by the manufacturer, and it contains also a specific information model, because it's more or less the information model that is contained in the automation component that you are buying. So we also talk about factory default state information model that is included here. What is also important, that we would require also a kind of connection to 6802. 6802 has defined a digital data sheet in order to describe the networking capabilities of a node, of Ethernet node. And this information is in YANG. It's modeled in YANG, and it's partly, I would say, we don't see it necessary to model this information in OPC UA or AutomationML. So we will offer a way to link or include digital data sheets into this product descriptor, and give then also the possibility to start up network engineering with the product descriptor. Coming to my next slide on the information model constraints. I would say with a rather general statement, a constraint is a restriction on an information model that goes beyond of only defining data types and structures. So it's an additional thing that gives you a more refinement on what you really want to do or what you really provide. And this can be additional range restrictions on values, it can be even dependencies between values that or you can restriction on structures. So something like also that if you select this option, then on another dimension, the values are changing, you can select as a next step. This is something typically where can be handled with constraints. And what you see here on the right side is a little bit, if you get the task to deliver this kind of code to a company, transportation company, and you only get the width and the height as the input data, you can end up with designing the wrong code, because in the end you need to fit into a kind of tunnel circle. And this is a picture from the tube. And so constraints give you the opportunity to refine your requirements and then make it more realistic that somebody else will deliver you the right thing. And as I said, these constraints can be used for selecting also the right product variant in a product family. It can be used to help assemble an I/O station from modular components. Typically, I/O station have some power requirements, so you can insert only that many modules that you don't exceed the power that can be provided. So this is a kind of logic where you sum up the power of the modules compared to the overall maximum. So this is not so easy to handle without constraints. You can also have a way to select in a device that can have multiple functions, the right functions, and depending on the function selection, you will select the right parameterization. And it's a way to guide and simplify offline engineering. And it's basically, I would say, logical rules that you add to the information model. So we see it as part of the information model. And of course, there would be some requirements to the engineering tool, because during engineering process, it would be needed that the engineering tool understand the constraints that are encoded in the information model and are able also to execute them in order that to give the customer engineer the hints that what he is doing is okay, or there are things that he needs to further resolve. Regarding the technologies for using constraints, we are thinking on some, I would say, variations that we would like to offer. We follow a kind of binary path where constraints can be formulated as like a binary. This is here the WebAssembly technology, or we have also thinking on using a logical language like Lua, that is a very smart, simple language to define constraints on an OPC UA information model. So this is just a glimpse on the work we are currently doing, and further information, I think this can be found in these links. What we also maybe would like to point you to this last link here. We have a tool, and this is constantly developed further, that helps you to create an AutomationML library from an OPC UA node set. So this is important, I would say, could be important for integration into engineering tools. We started working also into the opposite direction. So this tool, or we will have another project for that tool to bring AML information that was formulated with OPC UA back into a node set, whoever would like to have that. We're also working on tools for signature. As I said, a descriptor is signed, so we engineering tools would like to use a signing library for get a signature to their output. And we started doing here also some libraries. And what I forgot to say is also that we require for the signature also a timestamp, trusted timestamp server in the future. And this for that we are also working on the tooling. And so that would give a head start for members of OPC Foundation to use and integrate that in their engineering tool. That's already my last slide. Thank you for attending, and will be also available for the questions later.